And welcome back. Now we are starting an AI part of our stream. AI nowadays is a buzzword, I think, isn't it? Hello, Łukasz. Nice to see you.
Most definitely it is, but it's a buzzword that recently gathered a lot of attention from everyone. So hopefully during this presentation, I will explain a bit more about what I actually mean by AI in practical applications. I will present an overview of what robustness means and why it's important for you to care about it, what threats there are, and what kind of defenses you can deploy. So if you're looking forward to it, now is the time to log into the stream, call your family, call your friends, tell them to learn more about AI.
So perfect. And the stage is yours.
Thanks a lot. Welcome, everyone. I'm Łukasz Bartoszcze. I'm the founder of Control AI, which is a startup looking to help you with your compliance and robustness of your AI. We provide compliance as a service, but today I will be providing you with an overview of what kind of challenges you might find when deploying an AI in your company, and what kind of defenses are applicable in order for you to make the security profile a bit better, minimize the attack surface, and be sure that your models are operating as intended. So maybe let's start with why actually this is a big problem nowadays. If you look at the NGOs collecting the number of incidents, in recent years, we've seen over 1,200 different severe incidents of AI malfunctioning, and they have to do with both deepfakes being generated, used for spear phishing campaigns, identity theft and the like, high-frequency trading bots taking irrational decisions and leading to flash crashes on the financial markets, AI chatbots inciting violence or providing people with information on how to create the next Ebola, or giving them information how to create a bomb. So really, it's a global problem, and as we see adoption rates accelerating, more and more people start to worry about this. We've recently seen quite a lot of interest in the space from people who have served these models in production, who have experienced themselves how AI can operate not according with their expectations. And so companies have been putting into place different frameworks in terms of how they can ensure that their AI is functioning in a robust, fair, and trustworthy way. Still, the number of these ethical frameworks signifies that there is a lot of interest in the space. A lot of people are of the opinion that accuracy maximizing machine learning solutions are not enough, and that more needs to be done in order to actually make AI work as we expect it to and be up to standard that would enable us to achieve productivity gains, deploy it more widely, and basically enjoy automation, reduce the number of work while increasing economic prosperity. It's hard to say what robustness actually means. There are different definitions, both in literature and in those frameworks. How I'm going to refer it in this presentation and how I see it is the propensity of an ML model to function in production as it does in testing, as it does in the pre-production testing that you've performed internally within your company. It's not only companies, though, that are interested in ensuring that the AI models are tested, are validated, and continue to operate in a safe measure. There's growing interest from regulators, too, with the EU AI Act being enacted, and it's expected to come into force in 2 or 3 years' time. And the regulators have been increasing the fines for non-compliance for organizations that are opting out of those solutions, that are not validating AI, and that continue to operate as they are. Those fines can range from 7 to 10% of the global turnover of companies that are violating the provisions of the EU AI Act. And with so many different regulations also popping up in the US, in the UK as well, we are seeing growing interest into ensuring that the solutions that we deploy currently are more resilient, are more robust to failure. Nonetheless, even though, as I've shown you on this slide, there's a clear need for changing the existing paradigm, the existing status quo, where most people just build solutions and not really consider how they might fail, how they might be captured by adversaries. There's very little practical progress that we're seeing in the space. when we look at the business literature, we see that over 70% of companies that have made substantial AI investments in recent years report minimal to no impact on their day-to-day operations, which signifies that either they fail to complete those projects, or those models basically do not perform in production as they are expected to after being completely validated, after being implemented. We also see that despite lofty goals of those trustworthy AI frameworks and ethical AI adoption by multiple companies, only 21% of top executives report that they have actually operationalized technical robustness and safety. When we look at software developers surveys, 19% of them report that they have performed any kind of testing on their AI solutions. We believe that this is a cause of concern, and that shows that it's very hard on one hand to be able to complete those AI transformation projects, but it's even harder to actually test them and make sure that they will perform as expected and that no harms occur from getting them into production. When we look at the distribution of those incidents, of the people that are taking care of those issues, we see actually a puzzling phenomenon where the companies that would potentially have the highest potential to test their models, to implement those practices, and to actually develop unit tests for their models are the companies that have the highest number of incidents. From the databases on the NGOs, we see that the highest number of AI malfunction and incidents being reported come from companies such as Google, Amazon, Tesla, or Facebook, who have dedicated ML teams and for sure have much higher capabilities in terms of testing and validating those models than, let's say, a small AI startup or a Polish software house that maybe does not have a dedicated ML team. Still, we see that this is a growing problem, and that providers of foundation models that also have quite a lot of experience in the sphere, that would be well positioned for this, do not have easy, accessible measures of how to resolve those issues. And when we think about how the growth has been so far, as the technology evolves and we are able to increase the capabilities of our AI models, we are seeing even more distinct problems come up and distinct risks that we need to address. When we consider the complexity of general deep learning models, we've already had quite a lot of literature for 10 plus years on what kind of vulnerabilities they are, what kind of threats there are in terms of adversarial examples, backdoor attacks, poisoning attacks, side channel attacks, or even exploratory attacks. When we consider the rise in foundation models and the increased capabilities that they have, we see that not only have they not resolved the general deep learning challenges, but also bring a number of distinct issues that also need to be addressed going forward. And when we think about the use cases for both deep learning and foundation models in terms of how they can be perturbed and how they can be utilized, we can consider a variety of applicable use cases and a variety of attacks that could perturb many of the key core values that we want to address, and key use cases that can be perturbed within companies. They can range from computer vision models being fooled. For example, if you try to start a bank account and then there's some verification process on your iPhone that scans your facial features, adversaries could pretty easily mislead the model into thinking that their face, fundamentally different from your face, is pretty similar to your face, hence fooling the model and gaining access into your bank account or registering a bank account in your name without you ever knowing. When we think about chatbots, they have a high propensity for hallucination that could enable malicious actors to exploit it, to plant some information in there or leak your data, even if you haven't really consented for any type of data usage by those companies. when we think about regression models being used for insurance classification or determining whether you're going to get a credit, a bank loan from a bank, those could also be hijacked and leveraged so that they make incorrect decisions. Online recommendation engines. If you have a store, for example, in the form of Amazon, you can manipulate the user flow so that the AI algorithms suddenly start recommending different products that maybe the users do not really need and promote specific content online that could be not in line with the use case and hence perturb the operations of the service provider. So really, there's plenty of use cases that we need to be worried about, and specific goals of the adversaries can also be categorized into different buckets. What those are? Well, the obvious one is output manipulation. So basically, you have a model, it's working online, but the adversary submits a specific input and then causes your model to behave in a way that was not really in line with your expectations. That's the most obvious violation of robustness. And we're seeing this output manipulation being caused both in the form of self-driving cars being manipulated by patches on stop signs into driving the wrong way. Potentially could also be utilized for stuff like terrorist attacks and the like, to trading bots being manipulated by adversaries, by the adversaries submitting bids of $1 onto the market, hence fooling the model that maybe the volume is different and undertake the wrong decision, causing financial losses for the company that's operating this trading bot. Essentially, output manipulation refers to any kind of case where there's a vital operational result depending on the output of your model, and the adversary tries to circumvent it for their benefit. We're also seeing quite a lot of threats in terms of data protection in the form of data leakage, where the model has access to some private information of your company and is being exploited by adversaries to get access to this information, to get access to the information of your users, obtain credit card information, for example, or determine what contents were used as a part of the training set. And this has to do also with model stealing. That is the practice that we've seen in deep learning challenges 10 years plus ago already. But that has to do with obtaining the parameters of your model to deploy it for a competitor, or to basically launch a white box version of this model for yourself and then craft specific attacks on it to aid the attacker in conducting other types of attacks, for example, in the form of output manipulation. Furthermore, we're seeing one emerging category of threats as well in the form of performance decrease. That is submitting information to the model that might not obtain any vulnerable information from it or manipulate the output, but could have the result of decreasing the accuracy on other cases, or cause the energy consumption of your model to rise, hence increasing the cost for you. The energy consumption part can be done, for example, by specific inputs that do not change the output of the model, but that cause significant increase in the energy being consumed for the purpose of computing the specific output for the model. Hence, it's causing harm for your company, but it's very hard to detect cases like this, and you're bearing the financial costs of having to deal with the infrastructure stress. In terms of the accuracy that comes from the performance decrease, one example of this would be, for example, people crafting bots so that they log onto your platform, and when you're tracking the customer behavior within your platform, when you're trying to look at where the customers drop off, you're going to get incorrect information as a result of this pollution by bots, and take incorrect strategic decisions in terms of your infrastructure growth going forward. So all of those categories are threats that we need to think about when we deploy these machine learning models, and all have been a subject of growing interest in terms of adversarial and also non-adversarial defenses. Because when you think about it, all of those cases could also be a result of just your model malfunctioning naturally, rather than a result of an intent of the adversary. In terms of output manipulation, in the same way as an adversary trying to disturb the operations of a self-driving car by placing stickers, by placing adversarial input directly on the road, trying to perturb the operations of your car, we could have a situation where there is no adversary present and robustness is violated by the fact that you are dealing with out-of-distribution data, for example, in the form of foggy weather, and the cameras of your car not being able to properly detect what kind of signs are near the road, and hence being led into taking the incorrect decision. So robustness is both about thinking from the perspective of an adversary, but also ensuring that the operations of the model are in line with expectations when exposed to natural malfunctioning of the model. Same with data leakage, right? So it can be both an adversary that tries to attack a model, but it can also happen as a result of natural benign input being submitted by the user, and then the model just malfunctioning and exposing private information of the users as a result without any adversarial attack. And when we think about all of those threats, naturally, you might probably be a bit worried about what kind of defenses are applicable and why those models are still, why these problems are still present, why are models still vulnerable to this kind of attacks. And the problem is that there is no universal defense at the moment, neither in the deep learning sphere or in the foundation model emerging topic right now. So whenever we think about defenses, they need to be tailored to the specific goals and use cases of the model that we are dealing with. And usually, when we deploy those defenses, they only cover a subset of potential risks. So when we think about deploying a specific defense, we need to consider the risk profile and the kind of values that we want to protect before deploying them in practice, and then choose a defense that's applicable to this specific risk profile in order to maximize the utility of basically utilizing this model. What's also quite important in this case is that those defenses are not tangential to the operations of the model itself. So when you deploy a defense, often you're going to find that the performance on the original use case on the benign input might decrease a bit. So it's important to, for example, in the form of latency of your responses. So it's very important to consider those defenses and choose the optimal solution in terms of mitigating the threat on one hand, but also ensuring that the operations of the model are not completely disturbed as a result of you becoming more robust. There's plethora of defenses, and all of them have different strengths and disadvantages. So throughout this presentation, I'm going to be focusing on some of the key threats and the key problems that are currently in the machine learning literature and industry practice, and giving you a brief overview of what defenses I think are best for a particular situation. So let's start with a simple case, the most well-researched case that comes from the realm of deep learning and the time where we thought about computer vision models in isolation. So thinking about just a computer vision model that you train on your own data set, that you deploy for a specific use case. The main threat to those kinds of models are adversarial examples. How do they work? So basically, an adversarial example is a benign, is an example of output manipulation. So you start with a benign computer vision image, such as a pig, then you apply some sort of mask that modifies some of the pixels within this input, and you fool the model into classifying it incorrectly. Those adversarial examples, in a simple form, can take a shape that is pretty obvious to a human, choosing something that to a machine learning model might look different and cause misclassification, but to a human would be pretty well distinguishable. But the distortion that was achieved by state-of-the-art attackers is actually so small, the required distortion to cause misclassification, that nowadays most of those attacks are completely indistinguishable to humans. So even if you would have a human in the loop that would look at the samples being submitted, they would not be able to realize that the sample was perturbed in any crazy way, and would basically submit it as an input to the machine learning model, which is likely to misclassify it just by a couple of pixels being perturbed. And there's plenty of defenses being developed for these types of cases, in the form of adversarial training, defensive distillation, trying to train multiple networks that specialize in special cases, in special types of classification, and then using an ensemble of those networks to make the final prediction in the form of the mixture of experts defense. There's gradient masking, architecture search, multiple options available at your disposal to protect against this. Nonetheless, all of those defenses were broken, and actually the one that's currently most promising and the one that I would advise in dealing with adversarial examples is adversarial training. How does it work? Essentially, at the level of training, we create adversarial samples in the form of, for example, this pig being classified as an L-liner, and we add it to the training set of the machine learning model so that when it's attacked, it's going to recognize that this was in fact an attack, and something needs to be done in order to distinguish it differently from how the adversary would like it to be distinguished. The problem with adversarial training is that it favors offense. So you can only protect against a specific type of attack once you're already conscious that this attack is something that that might come up for you, and you cannot, like, once you craft, for example, an airliner pig here and you submit it to the training set, then the adversary can craft even more sophisticated model using the fact that you've already included this type of attack in your data set, and your machine learning model recognizes this type of attack and then attack it once again using the more sophisticated attack. So it's not a perfect defense, but it helps you a bit, and it's something that would enable you to protect the most vulnerable use cases, and try to create a simple defense that is pretty good in most use cases. Nonetheless, it will decrease the performance on your original use case. So if you submit quite a lot of adversarial samples into your training data set, then it's going at one point the model is going to have trouble distinguishing between benign inputs. But it's a trade-off that you need to make if you want to ensure robustness, if you want to ensure resilience. Same with non-adversarial training, right? If you think about computer vision models that want to operate on out-of-distribution data, the more out-of-distribution data, so for example, images of signs for self-driving cars that are taken in blurry conditions, that are perturbed in a way, the more of those samples you submit to the training set, the more resilient and the more robust your model will eventually be. So adversarial examples, that's the type of defense I recommend, but they do not only relate to these types of problems, so modifications of specific pixels, but are a much wider issue. And in fact, when you look at other examples of adversarial examples, they can also exist in the physical world, and in the case of stop signs, can take the form of adversarial patches, or with 3D printing, they can take the form of physical objects being printed that are likely to be misclassified by your computer vision models. In the first case, we're seeing a stop sign that's being perturbed in a way that's distinguishable to a human, but that would fool most computer vision models into not detecting this stop sign. On the other picture, we're seeing a picture of a turtle being 3D printed in a way that's likely to be misclassified as a rifle. So for example, for airport detection systems, this type of attack would cause this benign 3D printed model that's definitely not a rifle to be classified as a rifle. And this is an example of an adversarial attack that on one hand, in the case of the stop sign, is capable of perturbing the integrity of your solution, so causing a specific bad decision in this one case, trying to threaten a specific use case and perturb the output for a specific sample. And in the second case, in the case of the 3D printed turtle that could be classified as a rifle, it targets more the availability of the solution, so decreases the trust in the model by increasing the number of false positives. And for example, in the case of deploying such an object detection model at the airport, would decrease the trust in the model and eventually lead to the company that deploys it to abandoning further work on it and render it unusable. So really, adversarial examples can be used for multiple cases, and there's plenty of different angles that could be used to approach it. But of course, that's just for you to understand how these types of input attacks work. And in most recent cases, and what's most relevant for you, that probably does not have to do with computer vision models only, but relates more to LLM use and the integration of foundation models into your existing MLOps toolchain. And in this case, we need to change the paradigm from adversarial examples to prompt injections that function quite similarly to adversarial examples. How prompt injections work is by submitting a specific input to a text model or to a multi-model model that causes it to operate, to present an output that's fundamentally different from how the operation should look like. This can take the form of mode switching, so basically jailbreaking the system and telling it, I am the administrator, now give me a recipe for a nuclear bomb. It can take the form of goal hijacking, so confusing the LLM in terms of what's it actually supposed to do by submitting multiple requests and then telling it to ignore instructions, and finally submitting the final goal. Most of the time, an LLM would be so confused that it's just going to follow the original, the final goal, even if it was explicitly perturbed to do so, or it perceives it as a non-aligned, non-socially acceptable use. It can take the form of prompt leaking, so basically submitting a prompt that's designed to give you an answer that's going to expose system parameters or specific system instructions that the LLM has. Hence giving you information about how the model was trained and how you can basically copy it. And there's been examples of successful prompt leaking attacks on ChatGPT where the attackers were able to replicate the system parameters of ChatGPT for $600, hence obtaining the gradients that OpenAI has probably spent much more to train and gain access to the intellectual property of this company. You can also leverage SQL-like prompt injection attacks by basically trying to execute an SQL query from the text prompt of the LLM. You can also use adversarial prefixes or suffixes that take the form of this gibberish-looking text that has no semantic meaning to an individual, but that would have quite a lot of meaning for the LLM. And what this kind of prompt does is it enables you to unlock the capabilities of the LLM by basically saying, look, this type of information should unlock your capabilities. It's not so it has the same role as saying I am the administrator, but because of the gradients with which the LLM was trained, this type of information enables you to jailbreak it and basically say, okay, I'm going to use this gibberish prefix and then say do X, and the model does X. You can also just try random attacks, so giving it long strings of text in the form of, for example, repeating letters A. That would also cause it to malfunction. And in the case of ChatGPT, this attacks using AAAA give you the access to the training data set, and the model basically gives fragments of its training data set in seemingly random order, often exposing private information of users that have never consented to this, or queries that other people have submitted to ChatGPT. Not all of those prompt injections work at the moment, but what you can do is a number of defenses. The most prominent one being just filtering. So if you, it's quite similar conceptually to what we've done in the case of adversarial examples. Filtering looks at the output and the input of the model, and then looks at a specific prompt injection database in order to try to determine whether it's a malicious input and it shouldn't respond, or whether it's benign. So just like in the case of adversarial training, where we've looked at specific attacks and then we tried to make the model aware that it's an attack. In the case of filtering, you install a device that's going to look at the inputs and look at the outputs and try to prevent the model from executing those types of attacks, from just saying, if someone submits this gibberish looking like adversarial prefix or suffix, just saying, I'm not going to respond to this query. But once again, it's not a perfect defense, and in order to be able to leverage it, you need to have a good database of what prompt injection attacks you're actually trying to prevent and what these potential attack vectors are. So over time, I think that the threat here is that using these types of defenses is going to have the implication of you having to leverage those types of attacks and understand how they actually work. You can also use mixture of experts. You can also use reinforcement learning, but in the case of prompt injections, the only foolproof model that I'm seeing here in terms of defenses is a human-in-the-loop solution trying to verify those attacks and trying to be conscious of what kind of threats are there, in order to use this human layer of being in the loop, of looking at the output of the model, to reduce the risk of the model malfunctioning. What we're seeing currently is also attacks that do not take the form of text, but as we increase the capabilities of models and they start operating in multi-modal fashion, we can also see attacks that are prompt injection attacks, but that do not operate through text, but are using a combination of text and some other data modality, for example, in the form of image or audio, to cause the model into malfunctioning. So it's also a growing attack surface. And as we begin to see more multimodal LLMs being deployed, it's going to become a growing issue. So furthermore, there's also another problem of transferability. That is the fact that if you try to protect against those attacks, it's not enough for you to restrict information about how your model actually operates. In most of cases for deep learning attacks and for foundation model attacks, what the attacker can do is they can create a white box copy that's either coming from open source or they crafted it themselves of a particular attack, then compute the gradients of this attack in the form of some kind of prefix, suffix, prompt injection attack that's supposed to work with your model, craft a working attack, and then execute this attack pretty successfully on a black box model that you own that can have different training data set and different architecture. And because of the properties of the decision surface of those models, it's often the case that such attacks are highly successful, even if the adversary has no knowledge of the training set that you've used or the architecture that you've deployed on your model. In fact, this problem can get so bad as to the point where universal attacks can be crafted. So attacks that are not only transferable for a specific use case where an adversary tries to craft an adversarial prompt on their white box model and then transfer it to your model, but can be so sophisticated as to work on all types of LLMs. And we've seen suffixes like this being crafted where you create gradients for a specific open source LLM, and they can be applied universally, so work on all types of models, as you can see here, successfully perturbing ChatGPT, Anthropic, or Google's solutions without any problems. It's not only about directly controlling the input that the users can submit to your LLM. It's also about indirect prompt injection attacks. So how those function is they do not necessarily have a malicious input in the text itself, in the input itself, but they can be planted indirectly. So you can craft, let's say, a website that has malicious instructions for the LLM, or that has those adversarial suffixes or prefixes, and then you can, at the point of submitting the prompt, ask the LLM to retrieve information from this specific URL, hence poisoning the LLM and making it execute this malicious information, this malicious prompt that you've created. Those kinds of prompts can be very dangerous, and for applications that are integrated with those LLMs and are using this indirect or dialogue attacks can be a serious issue. Another example of how adversaries can leverage not only the output but also the entire ecosystem on which your ML service is being trained are backdoor attacks. So how do backdoor attacks work? The adversary can plant a hidden backdoor either in the data set that the model was trained on, in the model directly, if it's, for example, an open source model that you just download from Hugging Face, or on the serving platform that your model is hosted on, and then the model will continue operating as normally without the activation pattern. But once an activation pattern is recognized, it performs according to the wishes of attacker that has instituted this kind of backdoor. And we're seeing more and more backdoors being found in foundational models as well, and they can take the form of either adversarial patches, so hidden triggers that enable the attacker to modify the output of the model. For example, here, some gibberish text that can be planted in the data set that the model was trained on, so that the model is unlocked or behaves in a certain fashion once it recognizes this adversarial trigger, this gibberish that I'm giving it. Or it can be tailored to specific use cases. So maybe the model will perform well in all cases, but then the activation trigger would be some specific use case, like, okay, cooking a meal. If any user is trying to cook a meal, then you're going to give it some random, some bad, socially unacceptable output. So those types of attacks can be defended against in 3 major ways. The first one is to use models that you can inspect and trust. So do not use open source models that you have not validated, that you have no control on. If you're using third-party APIs that are pre-trained or are leveraging some kind of secret training data set or secret code, that's potentially an avenue through which backdoor attacks can be executed. Secondly, have control over the training data set. And that's actually the hardest to satisfy. As with LLMs, you basically train it on uncontrolled open source data sets of essentially all the information, large corpora of data, all information that's available in the internet. And so it's exceptionally easy for malicious agents to submit information to be used as backdoors in those kinds of data sets. And you also need to be mindful of using backdoors in the serving platforms themselves, and potentially having some harms from not being protected by the serving platform. So for backdoor attacks, I'm afraid that there's not necessarily a defense per se, but rather it requires a constant inspection of what kind of threats there are, and what kind of and what kind of steps you can take at the level of your ML system design to protect against those risks, and to be aware of what kind of challenges could be caused by them coming into place. So this concludes the part of adversarial attacks, of some of the attacks that I wanted to talk to you about from the perspective of the adversary. I also wanted to show you some examples of non-adversarial violations of robustness.
Łukasz, our time is up.
Okay.
So we have no time to other slides, sorry.
Sorry, okay.
We need to meet maybe tomorrow, maybe next year with it.
Sure.
But we have 2 questions, so maybe we can allocate 1 minute for questions, okay? Is it possible?
Sure, of course.
Perfect. So first question, are there any examples of AI compromised by terrorists? So by bad guys? Do you know anything about it?
I think it's a closed source solution, but examples of proliferation. So So basically, entire models being stolen and then deployed by hackers for malicious intent that, for example, in dark web, you can buy basically Worm GPT, a model that would assist you in attacking specific models. That's an example of how I would see it being used by terrorists, and maybe not specifically by terrorists, but jailbreaking them for the purpose of creating new viruses or attacking specific models. That's something that I would see. And then the second question is in terms of queries leakage. Yeah, so how I would protect it is by filtering, by using solutions like the LLM Guard, a solution that we're developing at Control AI that's currently open source, that enables you to protect against those type of personal data being leaked, credit card information being leaked. So basically having a database of what protected information means, and then if a query would cause a model to output this personally identifiable information or some other type of socially unacceptable response, preventing it from occurring. But it's very hard to do, and foolproof 100% security, I'm afraid it's not a word. So anytime we try to deploy those solutions, we need to be mindful of the challenges and the threats that are available, and take an honest assessment of what types of risks are involved. Potentially the only foolproof solution that I'm seeing at the moment, as mentioned during the presentation, is having a human verify the output, having a human in the loop. That's using this to automate, but that gives the final check before any decision is made or any information is released.
Thank you. So thank you, Łukasz, for your time, for your presentation. It was a pleasure to meet you. Thank you.
Thanks
and see you in the real.
See you in the real world. See ya.
See ya.